The next big idea in section 5.3 is finding the average value of a function. Remember back in chapter 2 we found the average velocity of a car or something. That was by finding the distance traveled and dividing by the time it took to go that distance. Well then, just a couple of sections ago we learned that we could find distance traveled by finding the area under a velocity curve. So here's a new expression for average velocity. It's 1 over b minus a, so divide by the time it takes to travel, and multiply by the area under the velocity curve, which is distance traveled. So average velocity over the time a to b is 1 over b minus a times the integral from a to b of the velocity function. And it turns out that this expression, this idea of finding the average value of a function, it's critical to the rest of our study of calculus, and it doesn't apply just to the velocity functions. It applies to all other kinds of functions. So this definition in this box is critical, and there's a place for it on your green paper, so make sure it gets filled in. The average value of a function over the interval a to b is 1 over b minus a times the integral from a to b of f of x dx. So let's think about what that means. You know how to find your average test score. You take all your test scores and you add them up, and then you divide by the number of tests you took. And that works because you take a finite, like an integer number of tests. So you have the ability to figure out how many tests there are, to add them up because it's not an infinitely long list, and then to divide by the number of tests. But if we think about finding the average value of a function, in general, a function most of the time has infinitely many possible inputs. So we still have that process of adding up all the possible answers and dividing by the number of answers. It's just that there are infinitely many possible answers. So and because there are infinitely many, we're going to have to use an integral to add them all up. Remember where that integral sign comes from? It was sort of a shortcut for sigma notation, sigma meaning add up a bunch of. And then the 1 over b minus a, that's sort of the equivalent of dividing by the number of x values that we've input into our function. And I want you to mention one more thing before we move on to some examples. If I showed you somebody's 6 test scores and I said, hey, guess their test average. Obviously you could compute it if I showed you all 6 scores, but you would be able to know really quickly, just by scanning those 6 test scores, you would probably already have a little bit of a feel for what the average would be. And you would know for 100% certain that the average test score has to be less than the highest test score and higher than the lowest test score. So this is the highest score and this is the lowest score. You know the average has to be somewhere in the middle. So I want you to think about that when you see an average value problem on the homework or on my test or on your AP test in May, because it will definitely be on your AP test in May. The average value of a function can't be higher than the highest possible output, and it can't be lower than the lowest possible output. So make sure you're getting an answer that's somewhere in between. So let's take a look at this first example. I think we've seen this wire problem before. I have a metal wire, and right here there's a heat source, and then the wire is coming out. So the wire is hotter near the heat source, and down here, 8 centimeters away, it's cooler. We've been asked to write an expression in terms of T of x, where T of x stands for the temperature of the wire as a function of how far away from the heater it is. So write an expression using T for the average temperature of the wire. So we can do sort of a direct translation. It says the average temperature of the wire, and we know that the wire starts 0 centimeters from the heat source, and it's 8 centimeters long. So essentially what we're being asked to do is write an expression for the average temperature of the wire from 0 centimeters to 8 centimeters. So in this problem, A is 0 and B is 8. And we're going to use T of x for the temperature. So if the average value of a function f from a to b is 1 over b minus a times the integral of f of x dx, then we know that the average temperature of the wire from distance 0 to distance 8 is 1 over 8 minus 0, 1 over b minus a, times the integral from a to b, so from 0 to 8, of, in this case, the function, the function whose average we want is t, so T of x dx. So that's the first step, is to write an expression using t for the average value of t from 0 to 8. So this would get you 1 point on the AP test if you wrote this much. The next thing we're asked to do is to estimate the value of this big expression using a trapezoidal approximation. So remember, a trapezoidal approximation, we're going to split this 0 to 8 distance up into little chunks, and we can see here from the table, did they tell us specifically how many? They said 4 subintervals, so that means there should be 5 data values. I'm going to use the data from 0 to 1. I'm going to use the interval from 1 to 5, from 5 to 6, and from 6 to 8. And for each of those intervals, I'm essentially finding an area, right? So I'm going to find the average of the parallel sides. In this case, it's going to be the average of the heights of the trapezoid. And I'm going to multiply that by the distance across the trapezoid. That's this distance between the input values, distance between the x values. So I'm going to, and don't forget, that trapezoidal sum that we're about to write, it's going to be an estimate for the value of the integral. And then notice that we have this 1 over 8 in front of the integral. So I'm going to write up the expression I would use. All right, so where does this come from? This is the 1/8 that I had here. Whoops. The 1/8 here is still in front, and then I'm going to add up the areas of, in this case, 4 trapezoids to approximate this integral. So this 1 is the width of the trapezoid. It's the distance between 0 and 1. Just like this 4 is the distance between 1 and 5. This 1 is the distance between 5 and 6. And this 2 is the distance between 6 and 8. And multiplied by each of those widths is the average of the 2 heights. So I have a trapezoid that has width, and it's got 1 height and a second height, and I find the average of those 2. So here, the first 2 heights are 193. So this is me finding the average of 193. So I get that this is equal to 75.6875. If you got 605.5, you've made a very, very common error, which is to use trapezoids to approximate that integral, but then forget that you have this 1 over b minus a that must get multiplied. And that's why I wanted to specify before we even started. If I ask you about the average temperature of this wire, and you know the hottest place is 100, and the coldest place on the wire is 55 degrees, then you know the average must be somewhere between 55 and 100. So if you get an answer of 605 as the average temperature, something's gone really wrong. So 75.6875 degrees, well, we've been asked to indicate units of measure. So the answer is degrees, because we measure temperature in degrees, so average temperature is also measured in degrees. But let's see where that comes from. Remember that an integral means adding up a bunch of areas of rectangles. So let's look at the units on the parts of this average value of a function expression. So 1 over 8 minus 0, if we're just going to examine the units, it's going to be 1 over, the 8 and the 0 were measured in distance from the wire. They're measured in centimeters. So 1 over 8 minus 0 has units of 1 over centimeters. And then that's getting multiplied by this integral. This integral represents multiplying a bunch of teeny tiny changes in x's times heights of this function, which happens to be temperature, which we've been told is measured in degrees Celsius. So this is going to be times degrees Celsius times, so that's the degrees Celsius is there, and this dx, that's a teeny tiny change in x. We'll look at what your x values are measured in. There's distances in centimeters, so centimeters. So, all right, so my units are going to be 1 over centimeters times degrees times centimeters, and you'll see that centimeters are going to, and 1 over centimeters cancel out. I'm going to get that my final answer is 75.6875 degrees Celsius. All right, here's a cool problem to practice using the average value of a function. If we have some intersection in some city and we know a function for the rate at which cars turn left. And this is actually from a released AP exam. If we know that traffic engineers will consider a turn restriction, that means they're going to consider putting in a stoplight at this intersection if the rate at which cars turn left is more than 150 cars per hour. So Part B says, traffic engineers will consider turn restrictions when L of t is greater than or equal to 150 cars per hour. I didn't write it in here, but this is in fact a graph of L of t. Find all values of t for which L of t is greater than or equal to 150, and compute the average value of L over this time interval. Indicate units of measure. So we've been asked to do two things. One, name the interval, the time values for which L of t is greater than 100 or greater than or equal to 150, and then find the average value of the L function over that interval. So that first question, it's not really a calculus question. We know how to do it. We learned how to do it on our calculator. So this is actually a graph of L of t. So when I've been asked to find where L of t is greater than 150, I'm just going to mentally drawing that line, y equals 150, and I can see that whatever the t values are there, that's where L of t is greater than or equal to 150. So you can practice doing this on your calculator. Remember, we're going to graph y equals 150. We're going to graph y equals 60 radical t sine squared of t over 3 on your calculator, and use the intersection function. You're going to find two time values at which L of t is exactly equal to 150, and then we can use our graph here to say, okay, well, it's between those two time values where L of t is greater than or equal to 150. Do not estimate the answer. If you've access to a calculator, you're expected to give an answer to at least 3 degrees of precision. So I'm going to write those up in a second. So my calculator tells me that L of t is exactly equal to 150 at 12.42831 and 16.12167. So a quick note, to get credit on the AP test, you're going to have those answers to exactly 3 decimal places. To at least 3 decimal places. After 3 decimal places, whoever's grading your test stops reading. But notice our next step is to use those answers as limits on an integral. And if they're only correct to 3 decimal places, your final answer might not be correct to 3 decimal places. So I'm going to recommend that you keep 4 or 5 decimal places, 5 or 6 decimal places in your intermediate work so that your final answers will still be correct to 3 decimal places. Okay, so that first part was to find all values of t for which L of t is greater than or equal to 150. So notice I've written that L of t is greater than or equal to 150 on, I'm using bracket notation, 12.42831 to 16.12167. And then compute the average value of L over this time interval. Well, the average value of a function L on the interval a to b is 1 over b minus a times the integral from a to b of L of x or L of t. Whichever variable you use in that inside the integral isn't going to be a big deal. This is what I would do. There are a couple of ways to write your answer. I would define, say I'm going to let a equal 12.42831. I'm going to let b equal 16.12167. And then the expression that I was asked to give is going to be 1 over b minus a, the integral from a to b, L of t dt. If you wanted to write those numbers out too, that's fine. You could have written the expression 1 over 12.42831 over 16.12167 times the integral from 12.42831 to 16.12167 of L of t dt. And then when I use my calculator to evaluate that, using funint, I get 199.4259. I've been asked to indicate units of measure. This is cars per, what is the time? Cars per hour. So the average value of a function is going to have the same units as that function. So that's one way to answer it. If L of t is measured in cars per hour, then the average value of L of t is also going to be measured in cars per hour. Or we can figure it out. This 1 over b minus a part, I'll underline that in red. B and A are time values. So this 12.42831 and 16, they're time values. So this is going to have units of 1 over time, and time in this problem is measured in hours. So 1 over hours times, what's an integral? It's a multiplication problem with whatever L of t is and whatever a small change in t is, whatever those units are. So L of t is measured in cars per hour. And dt, a teeny tiny change in t, a teeny tiny change in time, is measured in hours. So we have 1 over hours times cars per hour times hours. And you can see that 1 over hours and hours cancels out. And we have units of cars per hour.